It's time for mathematics, and today we will talk about cosets. I need some results about cosets to prove Lagrange's theorem. So let's say G is a group. If G is not a group, then forming cosets and all that is not very interesting. So let's take G to be a group, and let's take X to be some subset of G. Doesn't have to be a subgroup for now. Let's look at just the subset. So for example, let's take G is Z36 Z multiplicative. So it's the multiplicative group mod 36. So this group has a total of 12 elements. G, the order of G is 12, and we can work out the elements like this. All right, 12 elements. I think that's correct. I showed you how to do this in a previous video. And now let's take X to be just any subset. I chose it like this. So what we can do is take an element of G and we can form this new subset, G times X. So what I do is I take G and I multiply G times 11, G times 17, G times 23, and G times 31, and that gives us the left coset. And remember, the times here, the times is mod 36. Right, and I can also do a right coset, but it's going to give me the same thing because our group here is abelian, where G1, G2 is G2 times G1, because everything is just integers, multiplication, mod 36, that's abelian. But in general, you could have a right coset, which is different from a left coset. We will not look at that case. All our cosets will just be the left variety because our groups are abelian. All right, so what I'm going to do is I'm going to compute all the cosets. So for all G in big G, I will compute Gx, the cosets G of X, and I'll write all this down in a huge table here. That's the first half. Hopefully there are no mistakes. What I did was I took these elements and I multiplied by on the left by 1, 5, 7, and so on, like that. And I remember to use multiplication mod 36. Okay, so all of my numbers remain from 1 to 35. Okay, that was a lot of work, and this is what I get. I recommend you do this calculation also to get some practice. It's quite interesting. So these two, you notice that you get these pairs that form. It's quite odd. And the intersection of those two are null. I think this is true for all of these pairs. That's quite interesting. All right, so that's already the first phenomenon that we see. But there are some other interesting phenomena. For example, G is never in Gx. So, for example, 7 is never in this coset here. 25 is not in this coset. 31 is not in this coset, and so on and so on. That's very interesting, and we will compare that later to another situation. So that's one thing we notice for this case. And I can ask you to do a homework problem. So you choose some G, little g here, and you choose a subset X such that little g is in the coset Gx. So you try to find a situation like this. They exist, and you try to find one. We see that there are pairs that are totally disjoint, but can you find 3 of them that are totally disjoint? So can you find 3 of these cosets here, G1x, G2x, G3x, such that pairwise, here we have pairwise, they are disjoint, so their intersection is empty. And I don't think there is such a situation here. You examine this, or you do this calculation yourself, and you tell me what you think. So what that means is that you cannot find 3 cosets such that when you take the union of them, you'll be able to get back G. You can't really find that here. You think maybe it's possible because G has 12 elements, and 3 times 4 is also 12. So maybe it's, but it turns out it doesn't seem to work here. So you can't find a partition among these cosets. You cannot find a partition of G. So keep that in mind as we look at the next example. A natural question that comes to mind is this: what if X is not just a subset of G, but is actually a subgroup of G? And then what happens? Well, in this case, magical things happen, and you will see. You will see. So let's use the same group, the multiplicative group modulo 36. With, multiplication mod 36. But this time I will choose a different subset. So this subset is special. This is not just any old subset. This is actually a subgroup. You see that it contains the identity 1. X in the last section did not contain 1, so there was no hope of it being a subgroup, but this might be. Let's check. We fill in this multiplication table mod 36. Have a look at the entries of this table. The Cayley table is closed, and what does that imply? It implies that X is a subgroup of G. And why is that true? Why is this implication true? Because we proved it in an earlier video. I'll leave the links in the description box. Now let's calculate all the cosets. So for all G, little g in big G, we'll calculate G times X, and that's going to be a lot of work. There's the first half, and we see right away there are some amazing differences from the previous calculation. This and this coset are the same, whereas this one and this one, they're completely the same. And this one and this one, they are equal. So this is a phenomenon that's quite different from what happened before when X was just an arbitrary subset. We see more amazing differences. Pairwise, they are all equal like this. This is completely different from what we saw before. Let's note more things that are different from before. We see here that when the G is always inside the coset. So what we see here is G is in Gx. This is completely different. We didn't see this at all in the previous example, but we see it here in every case. So 25 is in the coset. G is in the coset Gx. So that's quite amazing. And we also see a repetition. It seemed that none of the cosets were the same in the previous example, but here there are only 3 distinct cosets. So there's 3 distinct ones, but there are 4 copies of each, and that gives me a total of 12. Okay, so what are the distinct ones? 1x, 5x, and 7x. Those are completely different, and those are the only ones that are different. And look at what's going on here. When I union them, 5x union 7x, I get back G. And look here, when I do pairwise intersections, they are all null, so pairwise they are disjoint. And what does this mean? Well, this means what you think it means. The distinct cosets here are a partition of G. That's amazing. And we can even use what we did in the last video and say that X defines a kind of equivalence because of this, because partition means there is an equivalence. I can call this equivalence, I'll do equivalence symbol with a big X on top. That's the subgroup that it's associated with. So I can say that 2 elements are X equivalent if they belong in the same coset, because that would mean that they belong in one of the parts of the partition together, and that is the same thing as an equivalence relation like we showed in the last video. Right, this is very beautiful and surprising. There was some interesting patterns when the coset was an arbitrary subset, but now that it's a group, the real magic starts to happen, as you can see, and it remains to prove all this stuff, which is what we're going to do next. Now let's start building up our proofs. We will assume that X is a subgroup of G. And the first thing we want to prove is that little g is always in the coset Gx. Okay, so X is a subgroup, and that implies that the identity must be an element in X, because that's just the way subgroups are. And now if I multiply both sides of this by G, I get GE is an element of the coset Gx. But GE is the identity, so GE is just G. So I have G is an element of Gx. And I'm done. Next one we want to prove is that the coset is identical to the subgroup X only when, if and only if, this G is in X. Okay, this is an important theorem. Okay, and let's prove this. So we prove the implication one way. Let's assume that it is true that the coset equals X. But this means that for all the little x, all the elements of the subgroup X, Gx is also an element of X. This is true because we know that G is an element of Gx, and so because they're equal, that means G is an element of X. So because of that and closure, G times X is an element of X. Since this has to be true for all X, I can choose X is E and see what happens. G times E is an element of X, or G is an element of big X, and that's what we want here. Great, so that's done. Now the implication the other way. Let's assume G is an element of big X. So again, for all the elements of big X, Gx has to be in X because X is closed. And so what we have here is the following. Gx, this is an element of the coset. This is some subtle thinking here. And so this is an element of the coset, and it's also an element of X. So that means the coset must be a subset of X. So think about that. Now we can continue this line of reasoning. For all X in X, then we must have G minus 1. The inverse of Gx must be in big X also, because G is in X, so that means G inverse is in X because X is a subgroup, but the product has to be in X too because X is in big X and X is closed, so this must be in there also. Okay, let me make some room. Right, so a chain of reasoning. X is equal to EX, but this is equal to G inverse X, like this, because G inverse, that's E. And this is equal to G, look at this, G inverse X, but this is in an element in X, and so therefore this whole thing is an element in Gx, the coset G of X. So if G, okay, what did we prove here? If G is an element of X, then, no, we proved, yes. No, wait. Okay, if X is an element of X, big X, then it is also an element of Gx, the coset X. So this means that X is a subset of Gx. But if I combine, that's hard. This is pretty crazy proofs. If I combine these two things together, I end up with the following, that X is it's equal to its coset. And that's this. Okay, so we did it. So we proved the if and only if both ways. Okay, let's do another one, a nice one, part 3. All right, Gx, two cosets. When are two cosets equal? So Gx equals Bx if and only if the G belongs to the other coset. So two cosets are equal if the generator of the coset, the G, belongs to the other coset. Of course, they're also equal if the B belongs to the gx, but it doesn't matter. 1 is good enough. So let's start by proving the implication one way. So let's assume gx equals bx. Then what can we say? Well, we proved from part 1, if you remember, proof 1, g is in gx, always true when x is a subgroup. So that means g is in gx, but gx is actually equal to bx, so g must be in bx, and we're done. We proved this. We got the implication. Now for the other side of the implication. I think this one is a bit more involved. So we are going to assume that g is an element of bx. So if g is an element of bx, there's some x in x such that b times x is equal to g. Think about that. So there's some element in x. When I multiply it by b, I get this g. And so I can write gx, the coset gx, this way, bx times x. But multiplying the x by some element that's in that x doesn't change anything. You can see that in the Cayley table. So this is just bx, okay? Multiplying a group by an element in the group does not change the group. So as an exercise, I'd like you to think about this. Let's say g is a group, little g is some element in the group. Prove that little g times g is just the same as g. So we use this fact here. So I'd like you to try to justify that. Okay, so I think that we are done with that one. Yeah, done. And it turns out it wasn't really more involved. It was pretty much easy also. And now 2 more proofs, and these are key proofs which are very, very important in understanding group theory. Let's say I have 2 cosets, gx and bx, then I have the following property. And remember, for these proofs, g is not just the subset, it's a subgroup. So we have either the following situations happen. Either these two are exactly the same, or they are disjoint. Okay, so that's very interesting. This is not what we saw with arbitrary set x, but this is what we saw. If we roll back in the video to the numerical example that I did, this is what we saw when g was a subgroup. Now recall proof 3 that we did above. If g is in the other coset, then the 2 cosets must be equal. Now let's assume this is not true, it's not empty. So let's assume there is something inside. We'll call it C. C is in the intersection of gx and bx, the intersection of these 2 cosets. So C is actually in Cx because this follows from proof 1. But we also know from this here that C is in gx. Okay, so because of proof 3 now, we can conclude Cx equals Gx. Now we can do a similar line of reasoning. B is in Bx, but C is also in Bx because C is in Bx here. And this implies by proof 3 again that Cx equals Bx. So, okay, combine these 2 together and you get Gx equals Bx. That's an amazing proof. So if let's try to understand this. If this is not empty, then they are equal. Okay, so there's only 2 possibilities. This is either empty or they are equal. The minute you have something inside here, they are equal. We showed it over here. All right, let's take stock of what we have shown from proof 1. Let me get my pen back. From proof 1, we know that G is in Gx, but this implies that if I take the union for all the G and big G and I union up all the cosets. I go through all of the elements. There's no coset missing a G. And so I get back G. So this is the union property. Union property. So part 1 of the proofs gives me the union property. Part 4, what we just proved here is that any two cosets either equal or disjoint. That's the disjoint property. Okay, and so together this proves that the set of cosets, I can fearlessly put in even all the duplicates, because the minute I put the braces around, I have a set, so there's no more duplicates. Sets do not have the same element twice. So this set of unique cosets is a partition. Partition of G. We did it. We proved this. It's an amazing thing. So when X is a subgroup, it creates a partition. And along with that partition, of course, it creates, as we showed in the last video, a magical equivalence that is special to the subgroup X. Very, very nice. All right, so one more proof, and this is another one that's very key, very important. This is proof 5. So all cosets of X have the same order. So if I have any two coset, G1 and G2 X, okay, when I look at the size, the number of elements, it's always going to be equal. Let's prove this. Okay, we're going to prove it in a little bit indirect way. We're going to show the following, that for all G in G, then the size, the order of Gx is equal to actually the order of the subgroup X itself. This is what we will show. So we will show this. And this implies this one, of course. Right, okay, get some more room. So let's define a function on X. For all X in X, let's define this function. H takes X and maps it on Gx. All right, so H is actually a function from the subgroup to its coset like this. Okay, and I can define again for, well, now for all Y in Gx, so all the elements in the coset, I can define this other function, K takes Y, and I'm going to define it like this, G inverse Y. Okay, there we go. And K maps Gx to back to X. If you sit back and think about this, you'll see that this is true. Now let's try to compose these functions. What is H composed with K? This has to be applied to Y. So that's H, K, Y, like this. H, what's K, Y? That's G inverse Y. And H is going to apply a G, G inverse Y, and that's Y. That's EY, and that's Y. Okay, so Y gets mapped to Y. So this is, in other words, this means that H composed with K is the identity function on the coset Gx. Very good. All right, so now let's look at the other way. KOH. KOH. It's like what Klingons eat, yeah? Isn't that koh or something like that? You know, they're not going to be eating fettuccine or whatever. They're going to eat goh. You know, okay. Goh is KHX. All right. K. Don't panic. Careful, slow, careful, patience. HX is GX. Okay. GX. And now K applies a inverse, G inverse here, G inverse GX, and that's X. Wow, beautiful. So goh is equal to the identity on X. And so because of this, then H, K, they're bijections. H is a bijection. So I have created a bijection between G, X, and X. And so therefore, I mean, if two sets if there is a bijection between two sets, then they are the same cardinality. The two sets have the same size. Well, we call that order in group theory. Okay, so in other words, X is equal to the order of Gx, like this. And so any two cosets will have their size equal to the size of X. And so this implies that the size of any two cosets is going to be equal to each other also. Okay, so we're done. We're done. Amazing. We're done. And so now what? Now we can prove Lagrange's theorem, which is really one of the jewels of modern mathematics. It's not just the jewel of group theory, it's the jewel of mathematics in general. It's just a very beautiful thing, very beautiful. As always, like, comment, and subscribe. Leave a question if you have a question. And very soon, I think in the next video, I will do the proof of Lagrange's theorem and apply it to something in number theory. That will totally astonish you. I guarantee it's something you've never seen before. Okay, until then, I will see you next time.